I'd like us to continue studying the polar form of complex numbers, which has already proved useful in visualizing an otherwise algebraic construction by giving it some geometric meaning. And what I'd like us to do is to consider two complex numbers in their polar form. So what I'm going to take is an arbitrary complex number z1 with modulus r1 and argument phi1. So I'm able to write this number as r1 times the cosine of phi1 plus the sine of phi1. And the second number would be similar. It would be r2 times the cosine of phi2 plus I times the sine of phi2. Okay, so I have two arbitrary complex numbers. Let's multiply them. If we do the same, go through the same process that we did when we multiplied complex numbers in their algebraic form, what we'll get is, well, the multiple of the moduli, r1 and r2. Then we have to multiply the cosine of phi1 plus I times the sine of phi1 by the cosine of phi2 plus I times the sine of phi2. And when we expand this product, what we'll get is, well, for the real part, what do we get? We get the product of the cosines, cosine of phi1 times the cosine of phi2, minus, because of this I squared, the product of the sines of phi1 and phi2. This is the real part of this product. The imaginary part, what multiplies I, will be of the form the cosine of phi1 multiplied by the sine of phi2 and the cosine of phi2 multiplied by the sine of phi1. So that is the real part, the imaginary part of that product. And what you might recognize, I hope you do recognize these expressions, the real part is actually can be written using the trigonometric identity for the sum for the cosine of the sum of two angles. This will give us the cosine of phi1 plus phi2. So this is exactly the cosine of phi1 plus phi2 plus I times the other expression, which is by the trigonometric identity exactly is the sine of the sum of our angles phi1 and phi2. So you can see what happens if we multiply complex numbers using their polar form. We can give the multiplication a very nice geometric meaning. What happens with these numbers is that let's say they are here and here. So we have two complex numbers. This is just an example, of course, with length modulus r1 and r2 and angles phi1 and phi2. What happens when we multiply them is that the moduli get multiplied, so the product will be really long, a really long vector, which will have modulus r1 times r2, and its argument, this angle, will be the sum of these two angles. It will be the sum of phi1 and phi2. So this is the geometric meaning behind the multiplication of complex numbers, and it was the polar form that led us to this very nice geometric interpretation. Now let's see what happens if these two numbers are the same. So if z1 and z2 are equal, well, to z, r times the cosine of phi plus I times the sine of phi, so this is just one single number. If they are equal, that means I'm squaring this number, and if I'm squaring this number, that will give me this formula a nice formula for the square of z by telling me that the modulus gets exponentiated, squared, and the argument gets doubled because I have 5 plus phi. So this is what happens when you square a complex number. The modulus gets squared and the argument gets doubled. So this is true in general for other exponents as well. That is the Moivre's theorem. So let me just state that theorem, the Moivre's theorem, which says that for all natural numbers n and complex numbers z, we have the following. We can express the nth power of z using its polar form as r to the power n, so that's the modulus exponentiated, times the cosine of n times phi plus I times the sine of n times phi, which means that the argument gets multiplied by the exponent. So this is the Moivre's theorem, and it gives you a very quick way of calculating powers of complex numbers. This can be proven using mathematical induction, so proof by induction works in this case. To finish the video, I would like you to try and calculate the following power. So let's calculate, well, take the number z to be root 3 plus I, and I would like you to calculate the length of z to the 100 and also the argument of z to the 100th power. Okay, pause the video, calculate these quantities, input them in the box below, and I will give you the answer after you have done that. Okay, I hope you pause the video. But first of all, what we need to do is we need to transform this algebraic form of z into its polar form. But that can be done quite quickly. If you calculate the modulus and the argument of this number, you will get, for its modulus, you will get 2, and for its argument, you will get pi over 6, so that is 30 degrees. So this is the polar form of our number z, and by de Moivre's theorem, if we want to find the modulus and argument of a certain power of a complex number, in this case 100th power, we just raise the modulus to that power, so it's 2 to the 100, and the argument will be multiplied by that number, so that's 100 times pi over 6, which can be also written as 50 pi over 3, which is 16 pi plus 2 pi over 3. 16 pi is 8 times 2 pi. 2 pi is 360 degrees, so that means we have to go around the origin 8 times, which leads us back to 2 pi over 3 when we add that to the sum. So we have to subtract 16 pi's from each of these expressions to get the actual argument of our power. So it's between negative pi and pi. I hope you got it right, and I'll see you in the next one.